I wanted to go through this removing duplicates problem. It uses, so I can, I mean, just before we get right into it, like the reason why it's useful is it uses like this, we call it like a pointer, right? There's like the solution can use like this, pointer type of thing, where basically it's like, all right, what by that I mean like, what element are you pointing to? And you can kind of increment or decrement, right? And you can kind of imagine doing that with just like maybe setting an index value and then deciding, okay, like, am I going to move the index up one, which means that now I'm pointing to this element. And if I increment it again, right, I'm pointing to this one, you can like decrement, right, and kind of go back in time. So like, you actually can see this a good amount in these LeetCode problems. But let's get into kind of what this problem is about. So I think the problem is, let me put it, make sure we get it exactly. It says, given an integer array, right, which just means like a list of numbers, return a list of all the duplicate numbers. But actually, we're going to go into the next one, which is we have sorted in non-decreasing, which I guess means increasing in order. So a list of numbers sorting in increasing order. Remove duplicates such that each element appears at most twice. Okay? So you can kind of see, right, if we do this whole, here's the problem, here's the solution. Here's the example, right? So this is okay, because it says at most twice, but something like this is wrong, right? Like, so we need to remove these extra ones here, and then this is okay again, all right? So what you can, like, in terms of how to solve this, basically we can, and it asks us to do actually like an O of n time, meaning basically we're going through this list just once, okay? So if we go through this list just once, one thing you can think about doing, because they're sorted, like how are you kind of doing this? Well, I mean, I guess you can count to see if like get a consecutive sequence, but then you kind of have to, and then remove. You could do something like that. You can do some like grouping situation. But if you just go one by one, you can imagine like starting at this index and then looking ahead two, right? And then going to this index and looking ahead 2 slots. So not this one, but the next one. And then going to this index and looking ahead 2 slots, right? And in this case, there's actually a map, right? What would we do here? We want to remove it, right? Because we know that if this is sorted and we have the current number and the current number looking ahead 2, and it's the same, then remove it, okay? So that's kind of the idea. Again, it would be the same thing. Now we're onto this. This is our index. Look ahead 2. It's the same. Remove it. Then go to this end, right? So this is why I say it's like this pointer solution. It's a little, let's just think about it. So we'll start doing this. So we'll declare index. And instead of actually looking ahead, I'll show you a reason why. We can instead just look behind. So we'll say the index, we'll start the index at 2. And then we'll compare for, we can say almost like the length of this list. So we'll go through I, and actually, you know what they'll do? Sorry, I'm going to do this a little bit differently. While I is, I think it's great. I'm going to have to code this out. Yeah, so while the length of the list of values is greater than the index. So basically what I'm saying here is like while when I get to when this index, if I'm going to be moving this index up, if this index exceeds the length of the list, right, we've gotten to the end, so we can stop, okay? So only while, index, another way of putting this is like index is less than, maybe that's an easier way of thinking about it. index is less than or equal to the length. I think it's the length of the values. Okay. Yeah, so that means that if index is, say, like 8, 2, 4, 6, 7, 8, 9, right? If the index is not is 8, so I'm gonna have to, my index equals 8, the length of the list of values equals 9, that's where we should stop, right? So where index is less than or equal to, once it's greater than, that's when we should stop, right? I think. Yeah, once the index, I think once the index equals, it might be, we're gonna have to see this. Okay, well, once the index equals the length of the values, once it gets to 9, that's where we'll probably stop, actually, right? Because then we're going to be over here. Okay, so while the index is less than the length of the values, what do we want to do? We're just going to compare. So we're going to do values. If values of the current index equals values of index plus 2. So what is this going to do? This will compare, or let's actually do a look back. We'll do values minus 2. Sorry that I'm making these mistakes. But it's like, what we're doing, and I can kind of show you down here, is we're going to compare these two numbers to begin with, right? Index is 2, values is 0. If these things are the same, then we want to delete it. If they're not the same, then we're okay, right? And we can just increment forward. So that's basically the logic right there. If the values are the same, right? If this equals this guy, right? Say this was a 0 here, then we would delete it. Then delete what? Values at that index. We'll delete this guy. Okay? Then what happens? Then we would proceed with our loop again, right? And now we deleted this element right here, right? That's 0. And now we compare again. If it's the same, we would delete it again. But in this case, they're different. So what do we want to do? In the case that these two values are different, then we want to increment my index. So we do index plus equals 1. So think about what this does. We can kind of like, first we can just probably do this. We'll just define this. I'll show you that. Hopefully it works. So we take my list of values, 0, 0. These guys have to get condensed, right? And then we're okay. So the rule is at most 2 duplicates. I probably have to declare this list too. You have to declare this list. So this is fine. And then we'll do index equals 2. Okay, and now let's look at the values. Right, so this worked. We started with our list. Let's just show it again. We started with our list of values here. We had 4 of these, 2, 3, 3. Then we called remove duplicates of values. If we want, we can return it, the list of values. And you can see, damn it. Did I do it right? I did it right the first time. Hold on. Oh, I did my return value here. Sorry about that. My return should be here. Yeah. So now you can see that this has properly removed these. So again, how did this do this? Let's just think through the logic. So we set index equal to 2. So we're here. We do a look back. So the third element compared to the first element. If they're the same, then we delete, right? If there was a 0 here, we would delete that extra 0. Then we go through the while loop again. If they're not the same, then we would just slide forward 1, right? Basically, we're okay. No need to delete anything. This guy doesn't have 2 duplicates, so we can just move forward 1. So now we compare this guy with this one. And you can see that's what I show over here. Is basically we say, does 0 compare to 1? It doesn't, right? No need to delete. So increment the index to 3. Then once the index gets to 3, we compare this versus this. Again, there's no problem. So we increment the index to 4, right? Now we 0, 1, 2, 3, 4. Compare 4 to 2. There is a problem, right? These things do match. So now we delete. We don't want to increment right? We don't increment at this point. We just delete this number, and that now shows me this compared with this number 1. So that's what's going on here, right? We stay at this index, this index of 4, and now, right, we've removed this extra 1 here, and we just look, 1 ahead, So that does the comparison, and then here again we need to delete, right? So this one will disappear. This index the index will stay the same. So this takes the new slot, this goes away. The 2 is now what we're going to compare with 1. No match, so we get to increment the index, move 1 forward, right? Again, no comparison, right? They don't match, move 1 forward, okay? And now at this point, we would hit that while loop condition where the index we're on is no longer less than the length of the list, right? Once this index is 8 or whatever, then we have it's 0, 1, so 1, 2, 3, 4, 5, 6, 7, right? We're at index 7, so we're at the end of the list. Okay? Yeah. Okay. So that's what this does. Okay, there's 2 things I think to point out. One is this pointer. I think that's kind of the main thing is this pointer solution where what you're doing, we're not I kind of fell into that trap. We're not looping through the list of elements. The reason why is because if you think about it, we don't always want, if we did a loop, that would always increment the index, right? And every single time. Here, we're only incrementing conditionally. All right? So, right, this is a useful technique. It can become even more complicated than this, but this is a good starting point. And it's good for things where it's complete in O of n times, just, look ahead. The other thing is for you to, now that you know the idea, right, after we're done, practice implementing this from scratch, right, because you want to feel comfortable, if you have this idea, actually coding it out. Questions about this? It can be, right, it can be complicated. It's not, I think the idea itself, thinking about it, I probably wouldn't think of it on my own, but now you can, know that this is kind of a LeetCode style solution, is just go one by one through the index and be careful, conditionally increment that index. Cool. Questions about this? Let me see. No? Yeah, Kyle.
So when you delete the current index, does the entire array sort of slide to the left? Is that the idea here?
Yeah, exactly. It's right. We delete, and think about it, that's also why it's useful. The way it probably would take some trial and error to implement it properly. it's like we're comparing this guy. Well, let's give this example. When we're at index 0, 1, 2, 3, 4, so we compare 4 versus 2. Now if we delete at this index, we're effectively now, it's like, okay, here was a duplicate. Now let's see if there's one additional, we want to get to this next value. It's not, we don't want to skip ahead. Like, we don't want to move ahead to here because there could be more than one duplicate, if that makes sense, right? Like, we saw that there was one, we're skipping ahead to this guy. Is there a duplicate? We still have to check if the element right here has, if I delete this, if there's another match between this current element. If there is, there could even be, delete it, there could even be another match. So we have to delete this element as opposed to this one, right? Because if you deleted this one, then you're basically saying, oh, I don't believe there's any more match, I don't believe there's any, I don't think it would work. I guess it just feels wrong to me to then move, say I'm all's clear, move to the next one. In practice, it might actually work.
It's clever.
Yeah. Like I said, basically, I think the only way you have to see this stuff, and then but the reason why we go through it is this is a pattern in LeetCode, right? These incrementing, decrementing a pointer. All right, so let's get into some data structure stuff, especially because, and the reason why I didn't know it is because of knowing about, well, now that we know about time complexity, it's important to understand how these data structures work, so then you can, understand, right, why certain operations take a certain amount of time. So, okay, the first thing is a list, and how, what does it mean when you declare a list, or what does it mean, and also what does it mean when you access elements of a list, right, things like that. So when you declare a list, the way that it works is Python will allocate, right, a contiguous space in memory, meaning it allocates a block of memory to hold all the elements. Normally it actually starts off with a smaller list. Here it says 10 elements, 10 elements, but normally it's 4 at a time, and it will allocate, again, you can think of it, if we start it at a location in memory, right? Where does this list actually live? Say it lives at location 100, right? There's just a memory address, and it's okay, we declare a list, my list equals this, right? Even though this list is empty, it's going to give us space so that we can have, 4 elements in this list, just automatically for Python. Okay, that's what I mean by contiguous, is that basically it's occupying the block from 100 to 132. So you can imagine that each element takes up 8 bits of space, right? So it's 100, 108, sorry, I probably did my math wrong, 116, so it actually would just be up to 124, right, if we allocate for 4 elements. Now, why does it do something like this? Well, if you think about it, it actually makes retrieval, if you at a specific element, very, very fast. So let's think about this. Let's say we want to see what is, if we just do something like this, my list and A, B, something like that, and we say what's at element 1, how long does that take? You don't have to go through every element, right? If we did more, C, D, you don't have to go through every element. 0, 1, 2, 3. Yeah, you don't have to go through every element to see what's here. Instead, we can just do a little bit of math, right? And we could say, okay, if I want to see what's in this slot, don't go one by one. Just do a bit of math. Know where the list starts. Starts at element 100. See that we're at the index, right? We said index 3. And just do 100 plus 8 times by the index. All right? If we want to do, say, my list index 0, where should we look? At 100, right? 100 plus 8 times by the index, which is 0, so it's at 100. We want to go to the first element, or let's say the second one, right? 0, 1. This is the second element. So we want to go to 108. That's where this thing lives. So this is very useful, right? Because lookup time by an index is what's called O of 1, meaning it just, regardless of the length of the list, it just takes one operation, right? It's constant time, always one step to perform this. There are other things that only take, yeah, Conwell?
Yeah, this list is homogeneous example you have. But what if the list is heterogeneous, like each element is a different data type?
Yeah, that's okay, actually, because really what happens is, let's say we do something like, say that the list itself is, we have a dictionary of like, Bob, name is Bob, right? Really what's happening, it still will, really what's happening is actually what's in the element is just a point, it just gives actually space for a pointer for this element to live in. You know what I mean? So it's not going to run out of space in terms of enough space for each element, because really what's happening under the hood is it's pointing this to it's in this slot, doesn't directly live the dictionary, but lives a pointer to the dictionary, and the dictionary lives somewhere else.
This is understandable for a dictionary, but what if it was a float or an integer, for example?
Yeah, it's fine. I mean, like is the concern running out of space or
No,
what?
the question is regarding the calculation. Will the calculation stay the same? I think it will be different. The way you did this 100 plus 8 into, wouldn't that change according to the data which is there in
Well, you
each
can,
case?
let's say right here it says, not, I don't think so, because like let's say it's like here you go to the slot and it says, hey, look in this location in memory, you know. So let's say this letter A as is at space 1000, right? And it says, okay, when you go to the slot 100, look to this location in memory 1000. So then you go there and you see the letter A, and we can, as long as we can put this, as long as we know, as long as you tell me where I'm looking, I can kind of create this. This could be anywhere, right? Like this could be, when we go here, look at location 3050, and then we say go to 108. We see 3050, and that's where Bob, this thing lives.
So when we say it is contiguous storage, it's actually contiguous storage of the reference. It's not the actual data.
Right, that's right. Yeah, that's
Okay.
right. It's actually, all it does is really just store a pointer to each of these, to each of the underlying objects or elements. Okay, so lookup time by index is very fast, right, with a list. Other operations that are very fast is, actually I have some diagrams, is removing from a list. So think about what happens here. Here I'm sorry about that. So here I'm showing, okay, let's say we have the number 1, we have the number 24, 48, 9, and now we perform the pop operation. What do? We just basically say the list ends, instead of ending at 124, just say the list ends at 116. Okay? So that's effectively how we're just changing the length of the list, right? Same thing if you add to a list, right? Now we pop, now we add. Say we append to a list. Well, we append to the end. That's very fast. You just add back in that 9, right? Like, as long as nothing's there, as long as this space is available, we're fine. Things that are, but this is not shifting, which means adding to the front of a list. That is not performant, or really cost n. has a cost of n. So let's just see why. Let's say we have this list, 124, 48, 9. We add to the beginning. So we add a 5 here. Every other element, right, the number 1 has to slide. We have to copy 1 over to this slot, copy 24 over to this slot, copy 48 over to this slot, copy 9 over to this slot, right? So actually adding to the end of a list is fine. Popping, right, removing from the end of the list is fine. Shifting, adding to the front of a list, removing from the front of a list also costs, n amount, all right? So basically performing operations on the back of a list, right at the end of the list, just takes one step, O of 1. Performing operations on the front of a list, takes n steps effectively, right? Because you have to change every element in the list, change the location of every element in the list. Another problem with lists is, right, this only works because they're contiguous, right? Because I know, right, the whole, the way this underlying benefit of fast lookup time by the index occurs because we can say, okay, if I want the second index, I can go directly to 116. So that means that, with this math operation, we need this contiguousness, right? We need to allocate a whole block of memory. But the problem that can occur is like, well, how long should this block be? So if we only allocate, here I'm allocating like 5 elements, and then you append, right? And then we allocate 5 elements, right? We have an image in the next spot, or like it could be anything. It could just be like a Python string or whatever. What do we do? Like, how do we append to this list? So what Python will do is it will basically copy over this list to a new spot in memory, and instead of allocating 4 elements or 5 in this example, it allocates a little bit longer. I think it's like 1 1/4 effectively. So we'll allocate like 8. And then if you run out of, if you keep appending, then I'll allocate another 1 1/4. All right. So that continuing copying, right? Think about what does that copying take? We have to go one by one. It costs n every time you copy. Okay. So that's another problem with lists, is basically running out of space, right? It will, that operation eventually will cost you n. Yeah, so popping, dequeuing, yes. So Alan's asking, in that case, would it be better to use collections dot, and I don't know how to pronounce this word. I think it's dequeue, but feel free to correct me, for popping or pending, as that provides O of 1 time complexity. That is correct. So we'll get into like what Alan's pointing out is like, all right, well, removing, right? Lists are very good at performing operations, either adding or removing from the end, but not good at adding or removing from the beginning. So in that case, you can use this from collections.dec. Isn't it just like from collections import dec?
I thought it was a key library. Isn't there a key library? Or am I
I think you can
mistaken?
do, let's see, import, is it just dec? I'm probably spelling it wrong. Not a good look. DQ. Oh, using DQ. Here they're implementing it from scratch, but you can. Let's see. I may have to just from collections import. Yeah, without auto completion. But there is a basically I forget what it is, but there is like I forget if it's maybe it is that. Huh? That did give me an autocomplete. DQ, and then can we just do DQ of the list? Something like that? Yeah. And now you can kind of insert, I think, insert and remove from the beginning of the list in O of 1 time as well. So this isn't, it's not like we use this every day, but and we'll get into this when we get into like stacks and queues. But like, when we're performing operations from the front, that's true. Like this is a way to get around that, right? So anyway, we don't really have to get into that right now. But for now, right, just know like, okay, benefits of a list is lookup by the index. All right. Performing operations, meaning pop, append, fine with a list, right? Performing operations at the front of a list, right? More costly. Basically takes n slots because everyone has to roll over, right? Roll down the list. And right, so and same thing with, it doesn't matter if you're shifting or popping, right? Every element is a moving one. And then also know that, one downside of a list is basically this contiguous space problem. Another problem with a list, right? Just to now transition into dictionary, like why do we have dictionaries and sets? What's the benefit? What if you want to ask the question, this, let's say we do this, we have a list. Let's just do letter E. And now we say something like, is F in the list? Think about what has to occur. You have to go one by one by one. What's the cost of this? N, effectively, right? You can do it, right? How can you do this a little bit faster, potentially? You can sort the list, right? If you do sorted of my list, and now we can perform binary search, right? Which is hard to implement, but just remember, but there's probably some Python function for it. But what is binary search? Remember, because we know the list is sorted, if you want to know, is the letter F there, what will I do? I'll choose the middle of the list and say, okay, here's the letter D. If because I'm looking for the letter F, I can now cut off, right? I don't have to look through anything here, and now I can split the list in half again, right? Until I see, get down to one element and basically say, is that letter, in this case, it's just like one operation. So I split the list in half, look at the letter D, and now I have left this portion of the list, and basically can split the list in half again, and now can look and see, okay, this is the last element, there is no letter F, just to make this a little bit better. So we have A, C, D, E, F, G, H, right? And we want to look for the letter I. Once the list is sorted, right, we can kind of pick a letter. Is I in the list? Right? We don't know, we'll just pick something in the halfway point. See the letter E. Now we know we don't have to look through all these elements, right? That's the benefit. Instead, you just look through this portion. Now we choose a middle part here again. So let's just choose these two, right? I'll choose the letter G. We don't have to look at F, right? We know that we have to go greater than that. And now we're finally at the end, and there is no letter I. So this is a benefit of kind of like, you can sort the list and then employ binary search. And that is, right, that's faster than, like, this actually costs n log n. But once your list is sorted, then this only costs log base 2, right, which you talked about, log base 2 of n. Okay? So meaning what? Meaning if this list is of length 3, let's do 8. Let's say 3, 5, 7, let's say it's J, 8. Right? The max amount of steps we would take is 3, right? Because 2 times by 2 times by 2 equals 8. Meaning if we split this list once, twice, right? Twice, and then a third time, we're down to a single element. Okay? We're down to the end, right? So that this technique, once you have a sort of list, right, can be beneficial. Still, it takes 3 steps. We can see with the dictionary, asking this question, is something in the list, that we can do that with a dictionary in just 1 step, effectively. All right. So the key thing to know is that index-based lookup, right, in a list is O of 1. Meaning, if you're just asking the question, my list, what's at index 2? That just costs O of 1. However, like element, right? Considering is this element in the list, that cost is O of n. Or you can do binary, for a sorted list, what's the cost? The cost is log base 2 of n. All right? Right? But like I said, implementing binary search is a pain in the butt, I think. But you can't write that. That's one thing you can do. All right, so a dictionary, if we use, and by dictionary I mean either a set, right, a set, or a dictionary. Here we're going to see that the cost is going to be O of 1, okay? Asking the question, is like the letter E in like my set? That just costs O of 1. Whereas with a list, it costs O of n. So why is that? So let's get to dictionaries. Right here. So the way dictionaries work, like imagine, actually work pretty similar to like the card catalog, right? Like the Dewey Decimal System in whatever, life, elementary school. If you think about it, like if you think of like looking at, like going to see like, is this book in my library? You don't go one by one like you would with like a list, right? And like, look at the first book, look at the second book, look at the third book. Like that's not what we do. Instead, we have a formula, basically, of where these books live, where I give you a book, right? Like, here, the Bible, right? I give you the Bible. What does that go? That goes in the religion section. I give you another book, Introduction to Physics. Where does that go? That goes in the science section, all right? So the whole benefit of this is that we have a formula, essentially, which tells me kind of exactly where, given a book, where does this thing get placed? And then when I'm looking it up, where does this book live? Okay? So that way we don't have to go one by one anymore. Now, one thing that can happen, right, is what's called a collision. So this is, by the way, using what is this? So this is a Dewey Decimal System, but the Dewey Decimal System is serving as what's called like your hash function. And all the hash function does is it takes an input and it outputs a location in memory. All right? So for instance, for the Bible, or we can do another one, Intro to Physics, right? That's outputting, I think, like 500 in this very simplified system. For War and Peace, right, given that input, it's outputting 800. All right? So that's effectively operating as our hash function. Given an input, right, like given this input, it will output a location. So one thing that can happen, which you probably are like anticipating, is, well, what if we have more than one book that needs to be stored effectively at the same slot, right? Like if our hash function outputs the same location in memory, right? So in this case, you can see I'm doing Intro to Biology. That should place me in 500, and now I have a collision, right? Because they're both allocated to the same spot according to my hash function. So what we do in that case is you just, in that spot, you store, what's really getting stored is a list, okay? In which case, the worst case scenario, like the worst thing that could happen when I'm defining my dictionary, is that actually all these books get assigned to the same location in memory because I have a bad hash function. And what that means is we're back to O of n lookup time to figure out, right? Like I'd have to, this whole thing, because everybody's stored at location 500, we have to again go one by one to see, is War and Peace in my library, all right? But in reality, we're pretty good at hash functions that in reality, collisions don't occur that often, okay? So, there's, if you probably at like a comp sci, they maybe you'd have to write a hash function, probably not even nowadays, would have to write a hash function, but like, one day, like 30 years ago, people had to define hash functions. And, they use different hash functions still today, right? But basically what you're trying to do with a hash function is, one, make use of all of the provided information by a key, and that way you have variance on the hash value. So what do I mean? Imagine our hash function just used like the first letter right here. That wouldn't, right? We'd obviously have lots of collisions. If we use the first two letters, right, we'd have fewer. If we use the whole string, right, we have, less likely to have collisions. So you want to use almost the entire key, right, as much of the key as possible in the hash function to say where this thing is being stored. The other thing is, map similar keys to different values, making collisions less likely. And then the third thing is we want this calculation of like given this string War and Peace, where's the location? We want that calculation to be fast. All right. Why is that? Because if we're using this hash function a lot, right, we want to be able to like add new elements to our dictionary, and for each element we add, for it not to take a long time. Okay. So once we have that hash function, right, let's say if it was just like add up the length of the string, well, then we just know, okay, like location, whatever this length is, 11, we go to location 11 in memory, and that's where War and Peace lives. And if it's not, think about how a dictionary works, right? So we'll have my dictionary, which is not how you make a dictionary, and we have like War and Peace. Okay, and now let's say I have some attributes, Dostoevsky, and whatever that guy was named, Raskolnikov. And then we now we want to retrieve it, right? So this is my setting of my key. So what is this doing? Using my hash function to say these values are going to be stored given War and Peace. Maybe it's like however long this is, right? At location 10, my hash function outputs location 10, stores these values here. Okay. Now I put in War and Peace. What does it do? Outputs location 10 in memory, goes there, and it finds these values. So again, one step. If we say now look for, crime and punishment, all right, this outputs, let's say, 12. We go to location 12 in memory. Nothing's there. Key not found error, right? That makes sense? So it just takes one step, right? Because the hash function specifies exactly where, or we just take each key, pass it through my hash function, it outputs a location in memory, right? And now we just go to that location. If it's there, we're good. We show you, we return to you what's in that slot. If it's not there, we return to you the key not found error. What about the time taken for executing the hash function for every, okay. Yeah, if you have to, so this is, remember, this is solving that problem for us, basically saying, is War and Peace, is War and Peace in my dictionary, like, is this key in my dictionary? So key lookup, right? Like key lookup, very fast, right? One spot, O of 1. If you're kind of saying, hey, I want to get all the values from the dictionary, right? Like I want to, here's War and Peace, here's Huck Finn, right? If I want to get like all the values and then kind of ask that question like, okay, do we have the author, right? And now I have to, then again, you're back to going one by one. So this is only for like key lookup, all right? Just know like a set works exactly the same way. So if I do like authors, and then I declare a set, right, of Dostoevsky and Twain, right, and Vonnegut, what is this doing? With a set, nothing's ordered, but we're effectively saying, we're passing this through a hash function, and we're saying, okay, Dostoevsky gets stored in location 100, right? And if I go and say is, Dostoy in authors, what do? Pass it through the hash function, look for location 100. If it's there, good. If it's not there, right, return false. So again, it's just one step. Okay? So it's like, this is where it gets to like, like if all you want to do is look to see a list of authors, you can just declare a set, and if what you care about is, okay, like, is this author in there or not? Then we would want a set. If we want to say like, what is the first author, right? Like by alphabetical order in the list, that's not really, that's there again, we're going to have to go one by one, right? That's not going to work for us. What would be better is maybe a dictionary, maybe a list, right? Sort the list, and then we know the first element of the list, right? So this is where like choosing the right data structure matters. Right? This is kind of why we're going through this. So this is element-based, right? Element-based lookup, right? Or key-based lookup with a dictionary is only one step, right? Because we're with a dictionary, with a set, we're using a hash function. We kind of ask the question, is Dostoevsky in my set of authors? It translates this to the location in memory and basically answers the question, is that there or not? Go ahead, Conwell.
Yes. So my understanding is the example you have War and Peace and Huck Finn. These are the values on which the hash function will be executed, and then accordingly the memory will be allocated. And it's highly likely that these can be in a single bucket or something. War and Peace and Huck Finn end up being under the same bucket, and then every nation we have to manually iterate through the array in which these words
but
to-
it's highly unlikely that they would be in the same.
Yeah, I mean that's not the concern. The concern is when you say the key lookup is order of one. My understanding was a hash function will be executed on this War and Peace value, and then it will accordingly go to a memory location for the corresponding hash value. And that makes sense. That makes sense that lookup. So suppose the hash value is hexa 1, 2, 3 or something like that. That lookup makes sense that is order of one. My question is the execution of the hash function. The moment you said, for example, the hash might be calculating the length of the string, which wouldn't be the case practically, but assuming that is still order of n.
If you want to, if you need to calculate, I think what your question was, was like, what if I go through every one of these keys? Like if I go through War and Peace and Huck Finn? Is that your question?
No. So my question is, the moment I created the dictionary, and internally the hash map has been
setting it.
Hash function has been executed, and all the memory has been allocated accordingly. Now, if in this any subsequent lookup, for example, I do lookup for War and Peace, my understanding is it will again execute the hash function to get the corresponding hash for this string, and then it will see if that exists in the dictionary, the actual allocated dictionary.
Right.
But then the step where we, again for each lookup, we execute this hash function. Isn't there some time involved in that?
For each lookup?
Or is that it is insignificant?
What do you mean you mean the time in the hash function? Or what do you mean?
Yeah, so starting from the beginning, like War and Peace. So the moment you initialize this dictionary, War and Peace and Huck Finn, these are the two keys. And regardless of the fact they end up in the same list of whatsoever location, but a hash function will be executed on War and Peace, and it will be also executed on Huck Finn, and accordingly the memory gets allocated.
Yeah.
And then that's fine. Now what you want to look up, you say my dictionary War and Peace. My understanding is, again the hash function will be executed on the string War and Peace to find the corresponding hash. And that is what takes order of one time, the hash lookup, not the War and Peace lookup, the corresponding hash. So yeah, in your example, suppose 10, as you mentioned. But getting this value 10 will still take some time, right?
Yeah, but it's
So is that insignificant?
it's
That's what I.
relatively it's basically it's insignificant. Like it doesn't vary based on the amount of elements there are, right? So you don't have to keep checking, right? There's really just one operation there. If you think about like, one operation for a computer to do, like normally just does not take a long time, right? And the hash functions are designed to be fast. So what takes a longer amount of time is, let's say we did not have this hash function, right? Let's say we had a list, and now we have my list of books. Going one by one, think about the kind of the operations. Each book, you have to kind of retrieve the book, or go to it, go to the location, see does it perform that equality, right? And like maybe return true or false. And now we have to do those operations for however the length of the list is. The other thing to remember is we care about this when we're in the like thousand, millions, right? Like tens of thousands, right? That's kind of when these things become a problem. So like executing a hash function, if we because if I just want to say like, is War and Peace, you kind of have to think about that. Is War and Peace, where we have, let's say, 1,000, 10,000 books, now I want to find some information about War and Peace. Cool, execute my hash function, get the answer, like we're done. Whereas with a list, we have to go one by one, right? And then maybe once we find it, search through it. Once we find it, now maybe there's a dictionary inside there that tells me about all the other attributes, right? Like that's kind of the point. So that's where, right, this time complexity really matters, as opposed to the cost of any individual operation is not very long. Yeah. One other thing to point out is, right, the same thing. So we said that this key lookup, right, that this occurs one with kind of dictionaries, obviously, with sets. This is also what's happening underneath with like indexes, right? It's a little bit more complicated than this, but what I mean is with like Postgres indexes. They're oftentimes operating like a B tree, but another way of doing that would also be, and the reason why they're oftentimes doing, remember that lecture we talked about, they're using like a tree, and the reason why is because oftentimes we need this data to be ordered. But another way that you could imagine doing that is like when we insert, use a hash function, right, and just have that be our lookup, right? And if I do, where the author is Dostoevsky, right, that can we don't have to then go through every element in the database, right? We can just go to the index, see the value, right, and then go to that location. So that, right, that's like another option for implementing an index. But like as we saw, it's not that simple because, right, we like the benefit of a B tree, of like the binary search tree, is that you can have the values sorted, or at least before and after type of thing. So this is like, right, so lots of times, so just think about it, right, like asking a question like, is this in the list, or sorry, is this in the set, is it not, right? That's where a set becomes very useful, a dictionary becomes very useful, right? Like asking those kinds of questions. What are dictionaries, right, like not good with? Things that involve like order necessarily, right? Like now I think Python has been upgraded so that it does order the keys. But typically, like classically, right, dictionaries are not ordering their keys. So if you want to see like what is the who is like the author in alphabetical order, right? That's not, a dictionary is not storing that. But with a list, we can sort our list and use the indices to impose order, right? That's the idea. Okay. All right. Cool. So what you guys should do, so a couple things. One, try to go through this removing duplicates, right? We talked about it. Try to implement it. Like without, I won't give you the solution quite yet. I'll deploy it later. Try to implement it as a first step. Next thing, we can go through these readings, lists, dictionaries, hash tables. At that point, then you can look again at the complexity of Python operations. I think they'll make a bit more sense. And then we can go through then a couple problems that use them. Another thing, I think I forgot to deploy this cold reachouts lesson. Just remember, like, this still, this is worth trying. I'll actually try to write each of you like a little pitch, because that's how nice I am, about like I'll look once we get your resume done, or even before it, I can try to write you all like a little pitch. And again, it's not going to be perfect. It's not going to be like what you shouldn't just copy and paste it because you want to customize it, but I can at least write some things of like, you can choose maybe a few of the bullet points that are most relevant and then tweak them to fit the position. All right. But this is right. If I do something like that, then that means that you guys have to actually use this stuff. So that, like I said, this has been the most effective way that I've personally gotten jobs, and then also have like helped students get positions, is right to the hiring managers. Recruiters are oftentimes not technical, so they just don't know how to translate your experience into the job. It's not personal. Like, I've spoken to plenty of recruiters. I don't have any malice towards them, but they've like told me, they're just like, how do I know if this person's good or not? It's how do they know? Like, really, if you're not doing the job, it's very hard to know. So like going straight to the hiring manager or telling them how, like, why you're a good fit, that's really what's important. All right, so we'll deploy these. I have the cold reachouts down here as well. Go through this, try this removing duplicates again. These things do come up, and then like the list, dictionaries, we can move through that next. All right, let me put you into